we now turn our attention to the red-black tree. Red-black trees are interesting. They have kind of a fierce reputation. They're used all over the place, but they're considered to be obtuse and difficult to understand. However, I think I have a good way that I can get you on board and really understand how they work. So let's summarize what we know so far. There are a bunch of different types of search trees, and we've seen two in our class. One is a binary search tree, and we know that one downside is they can get imbalanced. But the good news is we can somehow balance them using rotation, though we have no algorithm to actually do so quite yet. The other type of search tree we've talked about is the B tree. And I'm going to focus here on 2-3 trees. So 2-3 trees are balanced by construction. They require no rotations. You just build them and they're always balanced. So what we're going to do is something kind of strange. We are going to try and build a binary search tree that is structurally identical to a 2-3 tree. Now, I haven't defined exactly what I mean by structurally identical, but it should be a binary search tree that represents or is in some way structurally identical to a 2-3 tree. And in so doing, because 2-3 trees are balanced by construction, so too will our special binary search trees. Okay, so we're going to copy the behavior of a 2-3 tree, and if we could just do that somehow as a binary search tree, well, then we will get balance for free. So what do I mean by building a binary search tree that is structurally identical? Well, I'll start with a 2-3 tree which only has 2 nodes. So in this case, the corresponding binary search tree will be exactly the same as before. That is, here's a 2-3 tree where each of the nodes has only one item. And reminder, a 2 node is a 2-3 tree where the node has only one item. Okay? Now, where things become tricky is when we start having 3 nodes. So 3 nodes are nodes that have 2 items. And the reason it's called a 3 node, by the way, is because it can have 3 children, unless it's a leaf. So what do we do here? Here it seems like we're just stuck. There's no possible way to represent that as a binary search tree because this is a node which has 2 items in it and 3 children. Like, that's just not a thing we can do in binary search trees. But we can try and be a little clever and do something weird. And so one approach would be, let's create dummy nodes. Every time we have a 3 node, we'll create a dummy node and 2 nodes representing the D and F from our original 3 node. So ultimately, you could think of this outline shape as representing a 3 node. Okay? And in principle, you could do that. Now, the problem with this approach is that the result is, I would argue, inelegant. You'll notice that my binary search tree representation, it has an unused right link for D. And the reason is that this 3 node had 3 children, B, E, and G. Whereas if we look at this dummy node DF, like glue complex, I guess you might call it, it has 4 links coming out the bottom. So we're not using this link. And I find that a little weird. But hopefully you get a sense that something like this could work. Now what's done instead often is we instead create glue links. So instead of dummy nodes, kind of like a sentinel node where the value inside doesn't matter, we're going to create glue links. So anytime we have a 3 node, we're going to represent it by 2 nodes glued together by a red link. And here, because it's just a normal pair of binary search tree nodes, we're going to have here 4 total links. But one of them is going to be used to glue together the F and the D. So we avoid wasting a link, and we end up with a more parsimonious representation. Now, something like this is very often used in practice. The java.util.treeset, for example, is this basic idea. And so what I'm going to do for convenience is I'm always going to mark the glue links as red so that we can remember which links are equivalent to the connection between the 2 items in a 3 node. Okay. Now, if that seems a little confusing, I can understand that. But don't worry, we're going to get a lot of practice with this idea, and it'll make sense once you played around with it a little. Okay. So this thing we've just discussed, this binary search tree with glue links, is often known as a red-black tree. And now what we're going to do, inspired by the Princeton algorithms textbook, is we're always going to make the glue links off to the left. So it's always going to be represented with D below F if we have a node that's DF. Okay. Now, if you have these left-leaning red links, then the resulting object is often known as a left-leaning red-black binary search tree. Okay? Now, I should note that left-leaning red-black search trees are just normal BSTs. Okay? They don't, like, the red doesn't do anything special. It's just a convenient fiction so that we can remember which links corresponded to a connection between two items that were part of a 3-node in the equivalent 2-3 tree. Okay? Now, what's really important is that there is an exact 1-to-1 correspondence between a left-leaning red-black tree and its equivalent 2-3 tree. So there is, for this 2-3 tree shown, exactly one LLRB, and for any LLRB, there's exactly one 2-3 tree. So there's a 1-to-1 mapping, also known as a bijection, between these two different representations of the same idea. Okay? One other thing I should mention is that I usually omit saying LLRBBST because it goes without saying that if we're talking about a left-leaning red-black thing, it's going to be a binary search tree. So whereas you might have wanted to call this an LLRBBST, I'm just going to call it an LLRB. Okay. So LLRBs, they're just normal binary search trees. They behave just like a normal binary search tree. It's just that they are structurally identical to a 2-3 tree. So to test this and make sure that it really makes sense, and if you can do this problem, you understand the basics, I want you to come up with and draw the left-leaning red-black tree corresponding to the 2-3 tree that I'm showing. So pause the video, try it out, see what you come up with. Okay. So anywhere we have a 3-node, we need to have 2 nodes connected by a red link. Otherwise, everything is just exactly as in the 2-3 tree. And so when we do this, we see that our resulting LLRB, our binary search tree, it has a pretty nice structure, right? It seems, and I hope it's fairly clear. So if you understand this, you've understood what a left-leaning red-black tree is. All right, so in the next little bit, what we're going to do is talk just momentarily about the performance of these things, but make sure this makes sense before moving on.